So for the door hinges, the door is supported like this. So these are the door hinges. And this is the door frame. Okay. So this door you can rotate in this direction. So the hinge will allow the rotation. Okay. But just imagine you try to apply the force in this direction. Okay. Then you cannot move complete door from the hinges. Okay. And therefore this hinge will offer the reaction. This is the horizontal reaction. Okay. And if you apply the force in the downward direction, it will offer the vertical reaction. Okay. So here in the diagram, one application is shown for the hinge support. So this hinge support, this is used in the construction of the bridge. Okay. So this is the hinge point. It is fixed in the cement concrete. Okay. And this frame or this link, it can rotate in this direction. Okay. So this point will offer the reaction, like this is the vertical reaction VA, and this will be the horizontal reaction. Okay. So just from the calculation point of view, you should remember hinge support will offer two reactions. One is VA and second is the HA. Okay. So this is the free body diagram. Next support, it is the roller support. So roller support, it will offer only one reaction. Okay. And it allows the free movement. So this is the representation for the roller support when you draw the free body diagram. Okay. So here we have the beam AB or rod AB, and it is given one roller support. Okay. So the roller support, if you draw the free body diagram, then the reaction offered by this roller support will be like this. Okay. So this reaction will be perpendicular to the surface on which the roller is resting. Okay. So suppose this is the beam AB. Okay. And beam AB is supported at 2 points. It is supported at 2 points. At point B, there is hinge support. Okay. And at point A, there is a roller support. So when you draw the free body diagram, and let us take it is subjected to forces F1, F2. So in the free body diagram, first we will show the external forces as it is, and the reactions will be at hinge support. We have two reactions. So this is the vertical reaction VA, and at this point there is one horizontal reaction which is the H. Okay. At point A, it is the roller support, so there is only one reaction like this. Okay. So this is reaction RA. So you can see here the application. So this is the roller support. So at the point, reaction will be exactly perpendicular. So suppose this is the reaction RA. So such type of supports, they are used in the construction of the bridge. So the roller support, it will allow the free movement of the object. So you can see here, object can slide in the horizontal direction. Okay, like this. Okay, so you can see here, these are the roller supports. Okay, so when we construct the bridge, so on the bridge there are some joints. Okay, so these two parts of the bridge, they are supported with the help of the roller support. Okay, so the reason for giving the roller support at this contact is, so due to heat or due to rise in the temperature, there is a possibility that the material of the bridge, it will expand. Okay, and due to this expansion, this complete member, it will move in this direction. Okay, so in order to allow this free movement, it is supported with the help of the roller support. Okay, because roller support, it can allow the free movement in the horizontal direction. Okay, suppose instead of this roller support, if you add the hinge support at this point, okay, then it will restrict the free movement due to expansion. Okay, and that will give rise to the excessive stresses in this member. Okay, so in order to compensate the free expansion, we give the roller support at these joints. Okay, so this is the roller support given. So from the calculation point of view, you should remember roller support will have only one reaction in the free body diagram, like this. And next type of support is the fixed support. So fixed support means the member will be completely fixed, okay, with its surrounding. That is called as a fixed support. So fixed support, it will not allow any kind of movement. So there will not be any rotation, no horizontal movement, and no vertical movement. Okay, so it will offer three reactions. So here you can see, so these are the I beams or the metal beams, okay, used in the building construction. Okay, so these beams, they are directly fixed with the help of the bolt in this concrete wall. Okay, so this is called as a fixed support. So the fixed support, it is represented like this. Okay, so this is the beam AB. Okay, so it is the same beam. Okay, and this is the wall. So this is the fixed support. So this rod AB is completely fixed in the vertical wall. So now if I apply the force, okay, on the beam AB, then the beam AB will be perfectly equilibrium. Okay, there will not be any rotation, any horizontal or vertical movement. So at point A, we will show three reactions. So first reaction is there is no motion in the downward direction. So this is the vertical reaction, which is of VA. Just imagine if I add one more force in this direction. Okay. So this is the horizontal force. So because of this force, it will try to pull the beam AB in the rightward direction. But as this is fixed, so this wall will offer so if you add one force in the horizontal direction, okay, on the beam AB, then this wall will offer the reaction in this direction. Okay, so it will offer one horizontal reaction, which is the HA. Okay, and you can observe here this force F, it will create the moment about the point A. So if you take this perpendicular distance to be D, so the moment will be F into D. Okay, this is in the clockwise direction. So the effect of moment will be, it will create the tendency of rotation in the system. Okay, so this force will try to rotate the complete beam AB in this direction. But as this is fixed, okay, so the wall will try to oppose this rotation in order to maintain the horizontal position of the rod AB, and wall will offer the reaction in this direction. So this is called as a moment reaction. So moment reaction at point A. Okay, and because of these three reactions, HA, VA, and ME, this rod AB will be in the equilibrium condition. Okay, so fixed support will have three reactions: VA, HA, and the moment reaction, which is a ME. Okay, so these are the three types of supports for the equilibrium. Just we will summarize this. The first is hinge support. Okay, so hinge support has two reactions, HA and VA, and this is the representation. Okay, suppose this is A and B, and in the free body diagram, you will draw the rod AB only, and at this point, you will show the reactions. So this is a VA, and this is HA. Okay, so initially, when you draw the free body diagram, you can show HA maybe on left side or right side. Similarly, when you can change the direction of VA, you can show in the downward direction. Okay, so after using the conditions of equilibrium, that is summation fx 0, summation fy 0, okay, and the summation of moment 0, you will get the actual direction of HA and VA. Then second, it is a roller. Okay, so roller support, its representation like this. Okay, so roller support will offer only one reaction, which is the RA. So this roller is resting on the ground. Okay. So always remember the roller reaction is perpendicular to this surface on which the roller is resting. Okay. Suppose the roller is resting like this. The surface is inclined. Okay. And you have the beam. Let's take the same beam. So this is the roller. Okay. So when you show the reaction at this point, you should show the reaction like this. Okay. So this reaction will be exactly perpendicular to this surface. So here it is exactly perpendicular, and here this is the incline. So let us take this is RA and this is RB. Okay. And the last is the fixed support. So it will have three reactions: HA, VA, and moment. Okay, so point A, it is the fixed point for the beam AB. So when you draw the free body diagram, in the free body diagram, this is the vertical reaction, this is horizontal reaction, and you should show the moment reaction. Okay, so this is the moment reaction. Okay, so this is the fixed support. Okay, so now we will discuss the types of load. Okay, now we have seen the types of supports for the equilibrium. Okay, so here you can see the animation for the hinge support. Suppose we apply the force on the beam AB, which is supported by using the hinge support. So hinge support we can consider as a pin joint. Okay. So this is the pin joint. So if you apply the force, there is a tendency of the rotation, and it will completely rotate if you apply the force. Okay. But we cannot move the rod AB from this hinge point. Okay. So it offers two reactions, VA and the HA in the free body diagram. And the roller support, it will allow the free movement horizontally like this. Okay. So it will restrict only the vertical motion. So it will offer the reaction like this. Okay. So this is the reaction RA. And this is the fixed support. Okay. So it will not allow rotation and the free movement horizontally or vertical. So it will have three reactions: HA, VA, and the moment reaction. Okay, so what are the types of loads? So the types of load, we have first load as a point load. So meaning of point load is if the load is concentrated at a single point. The load means it is the force. Okay. So here you can see on the rod, there are two forces, F1 and F2. Okay. So these two forces, they are concentrated at this point only. Okay. So this is called as a point force, point load. Second example is if the object is pulled by a cable or by a rope. Okay. So here you can see we have the weight, which is a 10 kg. Okay. And we are applying some force by connecting the cable. Okay. So this is the cable. So the force, it will act on this object at this point. So this is again a point load. So this is the tension, suppose AB. Another example is, suppose one object is hanging okay. So at this point we will have the point load. Okay, so this is the point load, this is the W. So these are the examples for the point load. Second example, second type of load, it is the uniformly distributed load. Okay, so in short, this is called as a UDL. So meaning of UDL is, if the load is distributed uniformly over the length of a beam. Okay, so this is called as a uniformly distributed load. So this is the representation for the uniformly distributed load, and it is given as a W, and its unit is Newton per meter or Newton per millimeter. Okay, so the load is distributed across the length of the beam. So this type of load is used when we are calculating the reactions for the beams. So let us see how do we get the uniformly distributed load over the beam. Okay, so here we have one floor of the building. Okay, so while designing the building or these columns, so this is called as a beam, that is a horizontal member. Okay, so you must have seen such type of beams in the buildings. Okay, and this vertical member, this is called as a column. So while designing this column and the beam, engineers consider the amount of load will be acting on the beam and column due to the cement concrete of the floor and the load of the persons. Okay, so here we have just considered the whole area, that is this carpet area is covered by the person. Okay, so let us take this total area is 10 millimeter and 5 millimeter. Okay, and if you consider the small piece of this floor, which is made up of 1 by 1 millimeter. Okay, so this area or the cement concrete or the material in this area will have the weight which is equal to 10 newton. Okay, so each such area will have the same weight, which is the 10 newton. So this is called as a distributed load. Okay, so here we are considering a very small vector. Okay, because of 1 by 1 area. Okay, so in the 1 by 1 area we get the weight as a 10 newton. So if you consider the complete floor or this complete area of 10 by 5, okay, so you can consider millimeter per meter. So this total weight will be, this is 500 newton. Okay, and total area, this is 10 into 5, so it is 50 square millimeter. Okay, so distributed load in a 3 dimension, it is represented as a pressure intensity. Okay, so this pressure intensity, this is equal to 50 is the force, that is a net force, and the total area is 50 millimeter square or square millimeter. Okay, so it is 10 newton per square millimeter. This is the pressure intensity. So here you can see what is meaning of distributed load. Okay, so this load is completely distributed on the horizontal area. Now while analyzing this beam, okay, that means when we design the beam, okay, we will do the force analysis for these beams. So we have to just consider the force which will act across the length. Okay, so that is called as a distributed load or uniformly distributed load over the length. So this we can consider. So just observe from the side view. Okay, so just observe from this direction. So you can see the structure like this. So this is our initial beam. So this diagram is from the side view. Okay, and this is the column. So total weight due to all load is 500 Newton. Okay, so out of this 500 Newton, this column or the beam will carry the half load. Okay, so here you will see the 250 Newton and this will carry the 250 Newton. Okay, so this is the half load which is carried by beam on the left side and beam on the right side. Now just observe again from the front view. So you will have the beam which is exact horizontal. Okay, so here total weight is 250 Newton. Okay, so in order to visualize the distributed load over this length, okay, so actually on the beam along its length, we have the concrete. Okay, so this complete beam is covered with the concrete. So this 250 Newton actually it is distributed across the length. Okay, so we can find out this. Just divide the total load 250 Newton by the length. So this length initially it was a 10 millimeter. Okay, so 250 upon 10, so you will get the value as 25 Newton per millimeter. Okay, that means for 1 millimeter length there is a load of 25 Newton. Okay, and this is called as, so this vector diagram, it is nothing but the uniformly distributed or UDL. Okay, so right now its value is 25 Newton per millimeter. Okay, so unit of UDL is Newton per meter or it is Newton per millimeter. Okay, so I hope you understood the concept of distributed load. So similarly, uniformly distributed load, we have uniformly varying load. Okay, so uniformly distributed load, the intensity is constant across the length. And here the intensity, it is varying from one point to the other point. So this is called as a uniformly varying load. Okay. So at this point, we have the maximum intensity. So right now the intensity is given as a W Newton per meter. Okay. So here W, it can be 10 Newton per meter. Okay. And this intensity is gradually decreasing up to this point. Okay. So we can see such type of loads on the gate of the water dam. So here you can see. So this is the automatic gate which will open due to the water pressure. Okay. So water pressure, suppose we have the wall. Okay. And on left side of the wall, we have the water or any other liquid. Okay. So liquid pressure, it varies across the depth, and it varies like this, which is the uniformly distributed load. Okay, so there is one hydrostatic equation which is a P is equal to rho GH. Okay, so P is directly proportional to the height. Okay, so as the depth increases, the pressure will increase. Okay, so at the free surface of the water, that is at this point, pressure intensity it will be 0, and pressure intensity it is a maximum at this point, which is given by this equation rho GH, and therefore we get this pressure distribution which is a uniformly varying load. Okay, so same principle is used while designing this automatic gate opening mechanism. So here you can see this is the pivot point. Okay, here we have this stopper. Okay, so when the water level is below this hinge point or the pivot point, the gate will remain in the closed condition because of the stop. Okay, because the net force it acts in the downward direction, okay, or below this hinge point. So your moment it will be so when the water level is below this point, the net force due to this water height, it will act like this and it will create the moment in this direction. Okay. So this stopper will restrict the moment. So gate will remain in the closed condition. So as the water level increases like this, so you can see the position of this net force. Okay. So the force, its position will shift gradually in the upward direction. Okay. And after certain height, okay, that is the limiting height, this force will move just above this hinge point. Okay, and at this condition, this gate it will start to open. Okay, and then you can see the flow of water in the downstream side. So this is how the automatic gate opening mechanism works. So here just I want to show what is the uniformly varying load. Okay, so uniformly varying load. So at this point, you have the maximum intensity of the pressure. At the free surface, we have the zero intensity. So this is the distribution, okay, across the depth. And this is